So this is part two, and for part two of the exam, we need to make this graph using the method with the matrices and the solving with those that one matrix with the main diagonal having all of the 1 minus r's and then the minus r's on the upper and lower diagonals. And we're going to have some info here where we're going to have a step size of delta x equaling 1, delta t equaling 1, and having an alpha equaling 1, and an initial temperature starting at 20 C. This is the graph we are shooting for, and yeah, so let's get coding. So first things first, we need to start importing some these standard stuff. So we're gonna go import num_p as np. I'm gonna go from plotly, so we can make the plot itself. Plotly dot subplots import make subplots. Nope, that's not spelled correctly. Make subplots and import plotly.io as pio from scipy.io as, oh, nope, sorry. And this is what we're going, these two are just plot libraries and stuff. And this one we're going to enter something new just for this exam, and that's the solve Banach equation that's up here, where it takes those main diagonals and turns those into a useful equation for us to mess with. So scipy.linear algebra dot linear algebra, we import solve banded. Cool. Oh, we also want to template. We're gonna make this a dark default. So we can change it later. Equaling plotly dark. Cool. Wow, I can definitely not spell. Where did it say? pio.templates. I mess this one up every time. Sorry about that. Cool. So now it's time to get into the actual coding part. So what we need to do first is we need to have our constraints to the actual bar and situation itself. So we have nx, and that's going to be 50, which means we're going to have 50 sections right here. 50 sections from 0 to 49, and we're going to have our total time be 3600 because it's going to go by seconds, and it's going to go for a whole hour. So that means we're going to have our nt equaling 3600. Now for the constraints of the actual bar itself, we're going to have t be just an array. This is going to represent our bar. So it's going to be np.full. And that's just going to be size nx. It's going to be 20. Might as well put a period here. And now this means that the entire bar is 20, but we know that at the starting position, it's actually 50. So going on from here, we have the other constants, alpha equaling 1, delta x equaling 1, delta t equaling 1. That's just from the problem statement itself. And we remember from part 1 that we have our r equaling alpha times our delta t. And we're going to divide this entire thing by 2 times delta x squared. Now, this is our constraints for the actual problem itself, and now we get into the method of coding. So if we remember from part 1, how we do this is we have a matrix that's a one-column matrix that represents all of the temperatures throughout the bar at each distinct point. That's a single column matrix. And then we have a second matrix that is as long as our first matrix is 49 units long because we know what the starting position is for, so it's only 49 units long. So what we need is a matrix that is 49 units wide and some amount of units long, and that's going to be 3 units long. And that's because our first unit, if you look up here compared, we want these 5, 4, 3, 2, 1, 1, 1, 1, 1, negative 1, negative 1, or 2, 2, 2, 2. And we want these to be what we're making our matrix into. So how we do that is, or our top matrix is minus R, our middle, or our top row for our A matrix is minus R, our middle row for our A matrix is 1 minus 2R for everything up until the end because of that boundary condition we'll address later, and the bottom third row is also minus R. So how we do this is we have A equaling np dot zeros, and this is going to have size 3 and by n minus 1. Whoops, yeah, don't really want that. And then this makes it everything, but we know that there are a few special. This makes everything 0, but now we need to fill in with actual values that we need. So in the 0th column, or 0th row, going everything up, excluding the first column, we need it to be a value of minus R. In the first column, or first row, which is the middle row, because Python index says 0, we want the entire thing to be 1 plus 2R, 2 times R. And we also, but what we said also is the middle row is 1 plus 2R except for the last row, so we're going to address that as uh, 1 to negative 1, and that's going to be equaling 1 plus R. And finally, we want our last row to be, so of 2, and that's going to be the entire thing, and that's going to be minus R. So if you want to print out what A looks like, we see for the entire first row, we have 0, minus 5, which is negative R, and we have 0 as the first one because that's not, we don't care about this because it gets cut off. We have 2 for our entirety of it because that's what the value of 1 plus R is. Or I'm sorry, this is the value of what 1 plus R is 1.5. Meanwhile, 2 is 1 plus 2R. So, and finally we have minus R at the bottom. So that tells us that we have the correct values for A. Now we need the B matrix, which is the temperatures at some later time in the middle portions of the bars that we don't necessarily know. And represent that as a 0 matrix, np dot zeros, let's say nx minus 1. Because it's minus 1 because we know the starting temperature on the far left side here. We don't really need to include this one. So going from there, here we have a pretty good start. Now we just need to start the actual process of making the plot, this plot itself. So first things first, we need to make a range for all the x's so we can plot a nice set of x's. So a range, and that's going to be an x plus 1. That's not that. And it's plus 1 because since it starts at 0, if we type out what x is here, we get from 0 to 50. That's what we need. And then next is making our actual plot. We're going to have rows equaling 1. We're going to have a columns equaling 1. Then we're going to add our actual lines and make it a scatter plot. Fig.add scatter x equaling x, which is why we needed x, and y equaling t. And we're going to name this, I don't know, start, maybe? Yeah, start works. Cool. So now we have this, and here we go. We see this is the initial temperature of the bar where it's at 50, the immediately jumps down to 20. Cool. And now that we have this, we're ready to start iterating through the entire hour. So next we need to we're going to use a for loop. Wow. If you hear some beeping, that's my dinner being in the process of being made. Sorry about that. So we want to have some range of I, and the range of I is going to be nt, which is like all of t, since we made t 1 hour based off this. So that's going to be nt plus 1. And here is where we start changing and updating the value of b. So first we know about b is that, as we remember, when we're talking about b and how it changes, what we want is we want b to change from 1 to the left, 1 to the right, and 1 where it's at currently, have those be where it changes. So going from there, we want it to be the entirety of it, and that's going to be equal to r times t, where it's everything up to 2. I'm sorry, this is minus 2. Up to everything but the last 2 rows. And then we're going to add the 1 plus 2r column. So this was the first column of the minus r's. This is going to be the second column of the second column, or the second row of A. Sorry, and this is going to be 1 minus 2 times r times t. And this is ranging from 0, or from like the first position to the second to last position, depending how you want to say it because of Python. And we finally want to have t of the next one, so that's, it's like that. Cool. So if we want to print out b, it looks like this now, because now we're making it slightly different. Next thing we want to do is have our b0 just want to reiterate. So before we had zeros, and now at some time t, we went through and made all of these change from 0 to some value 20, which represents making up for the small change in time. Past that. So next thing we do is we have our B, our initial point B, and this is different and it has a different range, a different adding a different function we apply to it because it is at that boundary condition, so we don't actually need to calculate it the same way. Because once we do it at 0, we know what the, because it's all the way to the left at 0, we naturally know that the value is at 1 to the left of that. We know what that value is. We don't need to actually contribute that to the calculation itself. Finally, for the changes in B, we need to have the endpoint of B. And if you remember why we're changing this one, it's because it is next to the insulated point. So because it's next to the insulated point, we need to account that because we know it's insulated, the last point of B is actually just equal to something kind of like to the one to the left of B. So that manifests itself in 1 minus R to match the last row of T, the last element of T, the final row, final column of T, that element. Multiplying it by T, as you can see, minus 1. We're adding that to R times T minus 2. Aha, yes. I forgot the equal sign. This is 60 just for now. It'll work itself out in a minute. So going from later in, now that we have our corrected B's, we now need to actually use the solve banded equation. So that's going to be, we're starting at 1 because we know our actual T is, we know what our T is at 1, so we don't really care about starting at 0 because we don't want that to change. And here we're going to have it be solve banded. And the format for this is we need to have one upper and one, it's looking for one, how many upper, how many lower rows. We're going to have one of each, so 1, 1, and then A, and then B. And that's it. So after this, we're going to actually use now our T's to plot the point. But if I write T at this point, it should tell you all of the values. Fantastic. Because everything's so close. Only issues, there's like a little bit of inconsistency, but what can you do? Now, after we do this, we can now update the plot so it's not just the straight down line. So how we do that, if it's, since we want it every 5 minutes, we multiply and we're measuring NT in seconds, we just have it divide by 3, have our remainder be a clean 300. If, oh, whoops, if the remainder, wow, if i's remainder, which is a 300, is actually equal to 0, that means we have a 5-minute mark, and then at that point we can actually add the value of t at that time. So fig dot add scatter we're going to have x equaling x still. We're going to have y equaling t still. Equaling t. And mode is align. And the name is going to be, we want the name to indicate here like 60 minutes, 55 minutes, 60 and all that. So much like before, we're going to have it be f, and then it's going to be I. We're going to need to reference the variable I. But if you look at what this plots, it gets you. Ooh, wait, I'm sorry. Oh, wait, no, I didn't have the fig.show. Let me fig.show. Put out of the loop. So this is taking longer than I thought it would to show. So what I wanted to show is that it would show the seconds as just the number, but we don't want that. We want it as a minute. So I'm just going to change this how I want it to. So it's going to be np.int. So we're going to write this as an integer, base 16, or like 16 bytes, and we're going to have it be I. I'm going to divide that number by 60, so we get the number of minutes in that. There we go. Yeah. I don't know why I didn't do it before. And if you want to add minutes, you just append minutes on the end. And here, you get 6 start. Oh, okay. So we're going to actually change it to 0 now. Fine. 0 minutes. 0 minutes, 5 minutes, and then it ranges up like that. So that should be the end of part 2. Thank you for watching.